Integrals have various applications in chemistry, architecture, engineering, and many other fields. But today, we're going to talk about one of its applications in physics. Fluid pressure is defined as force per unit area, where magnitude of the force is acting perpendicular to the surface area A. Another equally important concept is the density. We all know the density of a substance is defined as the ratio of its mass and the volume the said mass occupies. It is useful in explaining why water pressure increases with depth. Now let's consider an incompressible water at rest inside a pail. Imagine a block submerged in this pail of water. This block has a cross-sectional area of A extending from depth D to depth D plus H as shown in the figure. Let us denote the pressure exerted on the top and bottom of the block as P top and P bottom respectively. In this case, the force exerted on the bottom is equal to pressure of bottom times A, while at the top is negative pressure at the top times A, since the force is pointing downward. Using the formula for density, denoted by ρ, we can say that the mass of the liquid in the parcel is equal to ρ times the volume of the liquid, or ρ times area times height. The weight of the liquid in the block, mass times g, the acceleration due to the gravity, is equal to ρ gha. Since the water is at rest, all forces sum up to 0, showing the popular formula P bottom equals P top plus ρ g. Moving forward, we now go to Pascal's principle, defined as the pressure exerted at depth h in a fluid is the same in every direction. To better understand this, let's imagine a plate completely situated at depth h with a pressure P top plus ρ gh. It's acting on every part of the plate. Everything flows smoothly as long as the plate is oriented horizontally at depth h. However, what happens when the plate is oriented in other directions? This is where integral calculus comes in. The Riemann sum approach is used in solving problems like this. Assume a vertically submerged plate that lies on the interval a to b inclusive on the y-axis. The force on a small portion of the plate is given by ρ gh times y times the function of y times delta y. All of these forces will equate to the total hydrostatic force given by ρ g times the integral from a to b of the product of the height and width as a function of y, with the infinitesimal changes in y as dy. Now that we learned how to get the total force on a submerged plate with the use of integration, let's proceed to a sample question regarding its application. A triangular plate is submerged vertically in water 1 meters deep. The base measures 0.06 meters, while its legs both measure 0.05 meters. If the vertex opposite of the base is located farthest from the surface of the water, determine the hydrostatic force experienced by the plate. Any ideas on how to solve this? Let's look at the figure first and examine the forces. Notice that the base of the inverted isosceles triangle should be parallel, and the height across the base is 0.04 meters by Pythagorean theorem. Let h and w be the depth from the base to the surface and width of the plate as a function of y respectively. Therefore, h of y is 0.96 minus y, and w of x is 0.06 plus y. We can now solve the force by substituting it to the formula. Take note that the bound should be from 0 to 0.04, since the plate is located at these range of y values. Also, the density of water is 1000 kilograms per cubic meter, and the acceleration due to gravity is 9.8 meters per second squared. The integral now becomes 9800 times the integral from a to b of the product of the quantities 0.96 minus y and 0.06 plus y dy. Evaluating it further gives the answer of about 29.43 newtons. I hope you had fun in learning the applications of integrals. Thank you for watching. This video is brought to you by Fishsticks. Check out these other math videos. Don't forget to like, comment, and subscribe for more quality content.